Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Aditya Mahajan. He'll be speaking on efficiently searching for good agent state-based policies in Dec-POMDPs. Professor Aditya is Professor of Electrical and Computer Engineering at McGill University, Montreal, Canada. He is a member of the McGill Center of Intelligent Machines, Mila Quebec AI Institute, International Laboratory for Learning Systems, and Gerard. He received the B.Tech degree in Electrical Engineering from the Indian Institute of Technology, Kanpur, India, and the MS and PhD degrees in Electrical Engineering and Computer Science from the University of Michigan, USA. He has held visiting appointments at the University of California, Berkeley, and the University of Paris, Saclay. Over to you, Professor.
Hello. Good afternoon, everyone. It's a pleasure to be here. I'm going to talk about some recent results that we have in the context of finding good agent state-based policies in Dec-POMDPs. This is something I'm really excited about, but I'll have to sort of explain why I'm so excited about this, and sort of two-thirds of the talk is going to be different approaches that we have taken for this problem which did not work, and that will help you understand why I'm super happy that this approach that we are proposing actually does work. And the motivation is looking at Dec-POMDPs, that is decentralized partially observed Markov decision problems, or multi-agent dynamic team problems. These are problems in which we have multiple agents. These agents get partial noisy observation of the environment, and they have to take actions which affect the evolution of the state of the environment. The key assumption is that the agents have a single reward function that they are trying to optimize, but the fact that they have decentralized information makes the problem extremely challenging. Why are we interested in this problem? The short answer is they come up all the time in almost all engineering applications. Let me give one motivating application which comes from network control systems. So imagine the problem of truck platooning. I have a bunch of self-driving trucks, and in this case, the fuel efficiency depends on the drag of the trucks, and the drag can be reduced by the trucks maintaining smaller distance between them. But if they're maintaining a small distance between them, then if the truck in the front brakes, the reaction time of the trucks behind them reduces. So an obvious way to improve that efficiency is for the trucks to have radios in that, so that whenever someone is braking, they announce their state over the radio and inform the trucks behind them that they are braking. This can go over multiple trucks. You don't have to rely on line of sight type of vision communication. But the drawback is that this communication would take place over radio channels, so there is some probability packets will be dropped. So I can never be certain that everyone has the same information, so there would be some probability that certain trucks have different information from others, while I still want to design a system which has some performance guarantees. So I just talked about all of that, and sort of in general, these things come up in different engineering settings. And the key features are that there are multiple agents. These agents have decentralized information. What one agent knows need not be known by other agents. We have the question of how to communicate or signal information. I can communicate information over direct communication channels, but there may be a band limitation or rate limitation in terms of how much data I can send. Or I can communicate information through behavior by acting in certain way which communicates to other agents on what I mean. And there is also aspects of learning. How do I design these types of systems when the system model is not completely known or not known to the same level of fidelity by all the agents in the system? In this talk, I'll focus on the first two criteria. And such decentralized control or team problems have a reputation of being extremely hard. This comes from some work in the 1960s and 70s. Perhaps the most famous of that is what is known as the Witzenhausen counterexample. Okay? And to understand why this had such a big impact, you have to think in terms of when this appeared. So this is in 1968, just around the time when the Apollo mission was about to make the moon landing. The technology used to control the rocket trajectory for the moon landing was optimal control. You do state linearization of the dynamics, use the theory of feedback control at that stage designed by Kalman in terms of using a linear state estimator to estimate the state, using a linear controller to design the control. And that theory was able to achieve the biggest achievement in mankind at that time to send man to moon. And Witzenhausen proposed a model in this paper, which was a simple two-step dynamical system with two controllers. The system dynamics were linear. The noise was Gaussian. The cost was a quadratic cost. The only key assumption was controller 2 did not know all the information available to controller 1. Witzenhausen in the paper identified everything is scalar, so fairly simple problem, identified the best linear controller and gave a nonlinear controller which performed better than the best linear controller. Okay? So this was sort of a shock because, as I said, the thought at that time was state linearization with linear control can solve all problems that we have. A few years later, Whittle and Rudge had a paper where they said, maybe, okay, so finding the optimal controller is nonlinear, which makes life hard, let's restrict to linear controllers. Okay? So they considered a two-agent problem in which they a priori restricted attention to linear controllers and showed that the best linear controller cannot have a finite dimensional representation. That means no matter what I do, I will need to have a complexity which is increasing over time. Okay? So maybe linear quadratic Gaussian is not a good framework. Let's just go to discrete state Markov chain type of models. There's work in 2002 by Bernstein et al., which looked at finite horizon decentralized POMDPs and showed that the complexity of finding the best controller is in NEXP. NEXP is a complexity class which is one class higher than P space, which is one class higher than NP. So these are problems in which the solution cannot be verified in polynomial time. And I require more than polynomial space to find a solution. Okay? So this is a really difficult problem in its most general setting. So the question is, why are multi-agent problems hard? Okay? So to understand this, we should ask the question, why are single-agent problems easy? So let's look at the simplest single-agent problem, which is Markov decision problem. There is an environment. There's an agent which observes the state of the environment, chooses an action, and this leads to certain dynamics which have a Markovian nature. And there is some per-step reward, which is the observation of state and actions. And in general, the agent can choose actions as a function of all the past states and actions. Right? This is the best that one can do. And I want to choose a policy to maximize the cumulative reward over a finite horizon. Now, the challenge here is that if I do a brute force search over all policies, the complexity is exponential in time. And the key question is, how do I efficiently search for a policy? And there are two results which allow us to find a policy efficiently. The first is Blackwell's principle of irrelevant information, which says that there is no loss of optimality in restricting attention to choosing actions as a function of the current state. Okay? Blackwell proved this in a nice 3-page paper in '94. Another result is, if I restrict attention to Markov policies, how can I find Markov policies efficiently? And this is given by the dynamic programming principle due to Blackwell. Okay? So what happens if I do not have full state observation? The setup is similar. What has changed is that my agent does not observe the state. It gets some noisy observation of the state, where this noisy observation depends on the current state, the last state and actions in some sense, right? Now, apart from this change that I'm getting a noisy observation of the state, rest of the model is the same. The agent is choosing an action as a function of the history of past observations and actions, and is interested in maximizing cumulative return. So same challenges, the brute force complexity is increasing exponentially in time, and I want to know how to efficiently find optimal policies. So the main result in partially observed MDPs is to look at the problem in terms of a belief state or a posterior distribution of the state given the observation and actions. The idea goes back to nonlinear filtering, where we construct nonlinear filters by looking at this conditional conditional distribution of the underlying state. And the main result is that if I look at a belief, the belief is something which gets updated in a state-like manner, and a belief is sufficient to evaluate the current reward. Therefore, when I look at the problem from the point of view of beliefs, I can actually pose a MDP, and therefore I can use results from MDP to argue that there is no loss of optimality in restricting attention to actions as a function of belief, and I get a dynamic program which is given in terms of belief. Okay? All right. So this is the case where we know things work and things works really nice. So what happens in the multi-agent setting? Okay? Let's consider the simplest multi-agent setting. So I'm going to assume that I have some same dynamics here which depend on state and action, and I get observations to the two agents which will depend on the current state. Each agent gets the history of its own actions, observations and actions, and chooses its action as a function of this history. Okay? There is a per step reward which depends on the state of the environment and the actions chosen by both agents, and we are interested in choosing a joint policy to maximize the cumulative rewards. Okay? Same challenge as before. Brute force search has a complexity which is exponential in time, and it's also exponential in the number of agents, but we'll ignore that for now because we are thinking in settings where there are few number of agents. And I want to know, can I find optimal policies in an efficient manner? Okay? I want to emphasize that I am looking at the simplest non-trivial setup of this problem. I am not assuming any strategic considerations. So there is no reward for agent 1, reward for agent 2, they are in a game with one another. That problem is horrendously more complicated than this. Neither am I asking what happens, how are the agents going to split the rewards amongst themselves. That leads to things like cooperative game theory, which is a bit complicated in the dynamic partially observed setting. There is no such considerations. There's a common single reward function. Both of them want to optimize that. There is no consideration of what we'll do after that. Okay? So the challenge is that there is a coupling between the agents, and different communities have different names for this. In the RL community, this is often called the non-stationarity problem. In the control community, it's called the second guessing concept. In the game theory community, it's known as signaling aspect of control, and so on. Let me explain what the challenge is here. Okay? So I know how to solve single agent problems. So I can say, let me look at the problem from the point of view of agent 1. Okay? If I look at the problem from the point of view of agent 1, then the environment and agent 2 are both a part of the environment. These are things that agent 1 does not control. And the history of the observations of agent 1 conditioned on histories of agent 2. Once both agents do this, I'm now in a different setting. Now, from the point of view of agent 1, if I go back to agent 1, the state of the environment is this, but the state of agent 2's history is the belief of agent 2 on the state of the environment and histories of agent 1. So agent 1 should update its belief to like that, and agent 2 should do the same thing. I continue this process forever, and I get this belief on belief on belief. Okay? So this gives to a complication in terms of how do I find joint sufficient statistics. Mathematically, one can show that this process will converge to some common probability space, but practically, I cannot work in this abstract space because I don't know how to actually construct these things properly. And it's not at all clear how I will use this for optimal control. So I think this picture really nicely explains what the difficulty is. We are trying to design one system where it depends on the other system, and that other system is trying to design something which depends on the first agent. Okay. So let's revisit the modeling assumption and see why things are going wrong. Yeah. No, because they have to be measurable with respect to different informations. A1 and the agent 1 and agent 2 have different observation. So I cannot choose action 2 as a function of data which is only available to agent 1. Sure, but I can consider that joint action, but I cannot do dynamic programming based on information available to both the agents, right? So I have to do optimization based only on data that is available to that agent. Okay. So let's revisit modeling assumptions, okay? And to me, one of the key modeling assumptions in centralized stochastic control is perfect recall. We make the assumption that an agent remembers everything that it has seen and done in the past. This is an unrealistic assumption. No real system can have infinite memory. But we make this assumption because it makes the analysis simpler, right? Once I make this assumption, I know that the belief state is a sufficient statistic. It gives me a compact sufficient statistic, a finite dimensional sufficient statistic to implement my policies. Okay? But in decentralized control, it is this assumption of infinite recall, which is, of perfect recall, I'm sorry, which is making my life harder. So an obvious fix is, let's not make that assumption. Let me assume each agent works with some finite memory. Okay? This could be a finite window of last observations. This could be a more complicated finite state controllers, or in a lot of implementation of these algorithms, this could be a recurrent neural network, which is updating the history into some compact statistic. Okay? So the key challenge, if I remove the assumption of perfect recall, is that I no longer have the Markov property. So how do I do optimization? How do I dynamic programming when I do not have the Markov property? Okay? So this is the question that we have been looking at for a while, that how do we find, I'm going to call this agent state policies in terms of the agent has an internal state and it wants to find a policy as a function of state. And we have been looking at this problem for a while. And I'm going to spend some time trying to explain approaches that did not work. So the first approach is something that we did about 20 years ago, which we called the designer's approach. This gives a very, very nice dynamic programming decomposition, but the computational complexity is hard that I cannot solve any problem beyond some few simple toy problems. Then we sort of, about 10 years ago, we started looking at what we called approximate information states to try to find approximately optimal policies. This works really, really well for POMDPs with agent state policies, but this does not really extend to multi-agent settings. And then I'm going to explain what is the recent result that we have in terms of searching for team sequential equilibrium in case of multi-agent settings. All right? So let's start with the designer's approach. So I'll go back to the same problem. I look at the decentralized POMDP, but I'm going to make an assumption that the agent is making decisions based on a local state, which I'll call the agent state, and this belongs to some set Zi. Okay? And at every time, the agent decides what action to take and what to store in its memory for the next time. Okay? And one example is this could be a fixed thing, so this could be a sliding window of last observations. But in general, this could be any function that I would like to figure out what to do. And my objective is then the same. I want to find policies where these things are chosen as a function of just the local state to optimize a cumulative reward. Okay? Same conceptual problems as before. The complexity is exponential in time. and how do I find good policies. Okay? So the solution that we have, which we call the designer's approach, is something very simple. So this is the system that I want to optimize. Let me think in terms of a system designer. This system designer does not make any observations. It's just thinking about how will I design this system before the system actually starts running. So it imagines this real system and says, when the agents have to act at time 1, this is what I'll tell agent 1 to do, this is what I'll tell agent 2 to do. Since the designer does not observe anything, what it has to tell to agent 1 is its policy. If you get this observation, do this. Same thing for agent 2. And it does the same thing at every time. And now the designer thinks, how do I solve this problem? This is the design problem that I need to solve. Okay? This design problem is a single agent problem. I want to do, how should the system designer design the system? So this is a POMDP. The unobserved state of the system is the state of the environment and the state of both the agents. The observations is empty. The designer does not observe anything. And the actions are the policies that it tells the agents on how to act. So I can write down a dynamic program for this. The belief state would be the distribution of the state of the system and the agent states of the two agents, conditioned on all the observations of the system designer, which is an empty set. So this is an unconditional distribution rather than a conditional distribution. I can show that this evolves in a state-like manner, and I can show that this is sufficient for evaluating the expected reward. Therefore, I can write down a dynamic program based on this. And this dynamic program, without going into too many details, would require at every time optimizing over the joint policies of all the agents. Okay? Yeah.
Constraint that if, for example, Z1 of t equal to Z1, but Z2 is changing, like we have maybe Z12 or Z22 or something, then in that case, because you don't want to confuse the agent 1 when you're designing, when the designer chooses this policy, so that I think your this probability distribution should have some kind of a constant value for different values of Z2, right?
No, this is just the joint distribution, right? So the joint distribution will depend on what happened in the past. Okay? Okay. So it depends on the policy, depending on what the designer had told the agents to do in the past, that will influence the current joint distribution, but it has no impact on this optimization problem.
Okay.
Okay? I'll solve this in the usual dynamic programming way, that for every realization of this joint distribution, I'll figure out what the policy is, and then I'll implement that policy. It's a POMDP in the sense that, from the designer's point of view, it's a partially observed system. It's a partially observed system in which I have no observations, but that's still partially observed, right? So it has the same, so this is the same dynamic program that I will have in a partially observed setting. The fact that I have no observation, what that means is that these dynamics are deterministic. That simplifies this a little bit compared to the most general setting, but it's still in the same difficulty class. Yeah. Yeah. Yes. Good. So the thing is, this is a deterministic dynamics. So I'm writing a deterministic dynamic program to find feedback policies, but I can implement them in an open loop manner. Okay? But I can also use some ideas from deterministic control to search for policies in an open loop manner. I don't really know how to do that in this setting, so I'm writing down a dynamic program which I know how to solve. And after solving a deterministic dynamic program, I can implement the open loop policies. Other questions? Okay. So the original version of this was proposed in Witzenhausen in 73, who called it the standard form. For POMDPs, this idea had been used by Sandel in 74, And we used it for general decentralized POMDPs. It has been rediscovered in different forms in the literature multiple times. The key feature is I get a dynamic program to find optimal policies. But in this dynamic program, the state is a distribution valued object, which we know how to handle. But my action space is also a function space valued object. And that becomes extremely complicated. Okay? So we have tried various approaches to try to solve this in an efficient manner. My conclusion at this stage is it does not work. Sort of whatever things we tried, we cannot get this dynamic program to work for any non-trivial problem. Okay? So the second idea. Okay? So it was, okay, let's try to understand what's happening with agent state policies, and let's simplify life a little bit. Let's get rid of the multi-agent setting, because the key issue is how do I deal with non-Markovianness of the dynamics. So let me consider a single agent POMDP with agent state policies. And to simplify things, I'm going to say that someone has given me how the agent state is updated. So let's just focus on how to find the control actions as a function of the agent state. Okay? Note that by successively unrolling this type of an update, I can say that the current agent state is some function of the history. Okay? Now, what we did was we asked when is such an agent state a good approximation for an information state. Okay? And the idea is it's a good approximation if I can identify two related objects. One object is an approximate reward estimator. This reward estimator looks at the agent state and action and gives me a reward. And I have a dynamics approximator which looks at the current agent state and action and gives me a distribution over the next agent state. I have these two things which are approximate in an appropriate sense. So I'll say they are approximate with an epsilon and delta if the predictive. That means that when I look at the true dynamics of the next agent state conditioned on, okay, this died, conditioned on history and action, that is a function of the agent state and actions. The distance between that in some appropriate distance on probability spaces is less than delta. Okay? So if I have these two properties, then we can show the following. So the idea is I have constructed this approximate reward and approximate dynamics, which gives me an MDP. If I have an MDP, I can solve the dynamic program, and that gives me a policy. And I can use that policy in the original model. Okay? Given a history, I find out what is the agent state corresponding to that history, and then I use the policy that I found from this approximate information state-based dynamic program in the real model. Okay? And the question is, how much do I lose in terms of optimality if I do that? So our main result is that I can show that this policy is alpha optimal, where alpha is a parameter that depends on epsilon and delta and some properties of the value function. So we can get this error bound, and now I can have an algorithm to actually learn good agent state representations. And what this algorithm does is take any reinforcement learning algorithm and add a block in that that tries to predict R, this dynamics of R and P, and take epsilon squared plus delta squared as an auxiliary loss in this reinforcement learning algorithm, and train your reinforcement learning algorithm in the usual way. Okay? This is a heuristic, but it works remarkably well in both Q-learning based algorithms and actor-critic algorithms. So we tried this in this relatively large class of environments which are known as mini-grid environments. So these are environments, for instance, this last one is key corridor. The agent is that triangle-looking thing there. I'm not sure whether it's clearly visible or not, but it can only look at a small part in some small zone around where it is standing. It does not see the entire thing. It cannot look beyond walls and so on. And this agent has to figure out that I need to go pick up that yellow key, go back, use that yellow key to open the door. Okay? Certain doors which have a circle in it can be opened directly. Doors which have dash in them, you need a key to open that. And it has to learn a policy which does this and open the door. Okay? So it's a fairly complicated partially observed environment with large state spaces and multiple entities and so on. And I'm going to try AIS, two variations of AIS, one based on MMD distances, the other based on KL divergence, and compare it with conventional algorithms such as doing PPO with an LSTM. And this is the type of behavior that we get. The green curve is the baseline of PPO plus LSTM. And what's interesting is that sort of roughly these environments are increasing order of complexity, that when I am in simple environments, all algorithms behave roughly the same. But when I start going to this complicated environment, which is the last environment of key corridor here, PPO is not learning at all. Okay? My environment has so many different features that even after 10 to the 7 iterations, the curve is completely flat. And that's because I want to have this completely random motion in order to be able to do a lot of these things in the right order to open the door. Okay? Interestingly, the AIS-based algorithms are able to learn. Okay? And they're able to learn relatively quickly. The same feature is observed if I do two Q-learning-based algorithms. So we have different types of experimental validation of Q-learning with AIS losses, and we roughly observe the same feature that when I go to complicated environments, basic Q-learning algorithms do not work, but if you add AIS losses as an auxiliary loss, you see good behavior. Okay? And to understand what is happening, this curve kind of gives a very nice illustration of what's going on under the hood. So what I'm plotting is that the blue curve is the episodic return during the learning phase. This is plotted on a logarithmic scale in terms of number of samples. And the red curve is the MMD loss between this distance that I had said in the model that I'm learning and the true observations. And in all of these models, what you see is that as I start learning, the MMD distance is reducing. And once the MMD distance is below a certain threshold, learning starts happening. Okay? So what this is saying is, once I have a good enough representation of what is going on, you see, I have to do a crazy random walk in order to get a reward. But once I do get a reward and I have a good representation, the representation helps me do credit assignment for that reward, and I update my Q function in a right way so that I can then start accelerating how the learning is taking place. Okay? I don't have an analysis or something like this, but this is what we observe in behavior, and this is very, very encouraging because we can solve these complicated POMDP environments in a relatively simple, unified way. Okay? How does this work for multi-agent settings? Okay? So that was our original question. And there are some things we can say in terms of common information approach based for multi-agent systems, but it really does not work in general. Okay? And the key difficulty is this is an approach which is based on dynamic programming, and I cannot really do dynamic programming in a general multi-agent setting. So a dynamic programming based approach is not going to work for multi-agent setting. Okay? So back to the design board, how can we get something which works in the multi-agent setting? Okay? So what we are going to do is relax our objective. Okay? So I've tried different things in order to find a policy which gives me either optimal or approximately optimal. Nothing seems to work for the multi-agent setting. So let's give up on optimality and ask local optimality. Okay? So I'm going to go back and look at how information decentralization is handled in game theory. So let's consider what is done in games with asymmetric information. Suppose I have a game tree, and I have two histories which belong to the same information set. And I have two actions at this history, either go left or go right. And I want to figure out what is the Q function at that information set for going left and going right. The difficulty is I can figure out what happens when I go left in the first tree. I can figure out what happens I go left in the second tree. In order to say what happens at that information set, I need to average over these two things. Okay? So what is done in game theory is said that for every information set, I'm going to come up with a belief system. That belief system tells me if I'm in this information set, what is the probability I'm at history H1, what is the probability I'm at history H2. And then I'm going to average things according to that belief system. Okay? So this gives me a way of computing Q functions under partial observation. And all the notions of equilibrium in games with asymmetric information says that equilibrium is not just a strategy, it's a collection of a strategy and a belief system. And I need my belief to be consistent with strategies. So beliefs should be a function of strategies, beliefs updated according to Bayes' rule. And then strategies are best response to the belief. That when I'm saying at this stage which strategy I should do, I do averaging at different points in my information set according to the belief that I have assumed there. Okay? Yeah. Yes. Yeah. Mm-hmm. Yeah, so I'm not observing the state transition of the true world. I'm observing the state transition in this AIS space. So sorry, this doesn't work. So I'm observing a state transition on this compressed thing. So in my RL experiments, I'm saying I have a recurrent neural network, and I'm going to assume a dynamics which tell me what is the next state of my RNN, given the current state of the RNN and the action. So that's the dynamics that I'm observing. I'm the observation, the next, I'll get the sample from the next Z will be observed. So when I do this realization of this variable will be observed. I'm taking a parameterized form of this, and therefore I can learn the parameters of the neural network to optimize this. I mean, there is still this that I'm not getting this distribution, but samples from this distribution, but I can do this part. Yeah. Yeah. Two players, they get some noisy observation of the state. That's it. In this case, it's in sort of in this case, I mean, this is not two agents. It's just there are two histories, and what this notation type of means is these shaded things means these are things which could have happened in the past, and at this stage, an agent has to act, but it doesn't know which trajectory has been realized in the past. The observations that it had tells it it's either history 1 or history 2, but it doesn't know which the true history. So this is, yes, so in this graph, it's not multi-agent, it's just what happens for a single thing. It's not, because the trajectories depend on the strategies of the other agents. So in the general dynamic game setting, you have a game tree. You specify, and what you have information sets which tell me each agent could not figure out when it is turn to move which of the two states it is. And I have to figure out a strategy for everyone. So at every information set, how should an agent act? And the difficulty is, in order to do policy evaluation, I need to figure out what is going to be the probability of being in one node versus the other. And the way in the way game theory resolves this is by saying, let me separate the belief system from the strategy space. So that's what I'm saying, that this is what the separate belief system part means in the game theory terminology. Okay? But in the multi-agent setting, every agent will have something like this on multiple information sets. So the issue here is, typically in games with asymmetric information, the assumption still is agents have a perfect recall. And that's the reason when they say we are going to update beliefs, beliefs are conditional distributions. It's the distribution probability of being in history H1, given that I have seen things which tell me I'm in information set I. Okay? How do I define consistency when I do not have perfect recall? Okay? So, sorry, just different things which use this as Bayesian perfect equilibrium and sequential equilibrium. And the difficulty I have is how do I define a belief system when I do not have the perfect recall. Ignoring that, I can ask that I'm now interested in finding what I'll call a team sequential equilibrium. Team sequential equilibrium will be a collection of policies and a belief system, and I will want two properties. That I should talk about sequential rationality at any instance in time. The policies that are being played at that time are best response to the beliefs, and the beliefs should be updated in some consistent manner. Okay? If I can do these two things, I have a notion of a sequential equilibrium, and we'll see if we can compute this. Okay? So what do we mean by Bayesian update when I don't have perfect recall? So I don't need Bayesian update, right? I just need to define some belief some distribution according to which I'll do averaging. So let's track unconditional beliefs. I just track the joint distribution. Okay? So this gives me my algorithm. So this is what I'm going to do, and just to simplify notation, I'm going to use xt as a notation for state, the observation of my agent. This is for the POMDP setting still, and zt is the agent state, and ut is what the agent is determining, next action and the next agent state. And the key observation is, although zt is not an Markov process, xt is a Markov process. If I combine the environment state and the agent state, that together is Markovian. However, when I look at the policy, I cannot choose a policy as a function of the environment state and agent state, because the agent is only observing the agent state. So the policy has to be a function from the agent state and agent's observations to actions, but I can evaluate this policy on this original Markov chain. So I can do the following. These are the different processes over time. I can do a recursion backward over time, where I start with a terminal Q function, which will depend on the state and actions. And I go back, and I keep on recursively computing these Q functions as a function of the policy. Okay? This is the standard policy evaluation formula in MDPs. Okay? Once I have done that, I can do the second step, which is a forward pass. I can start computing the marginal distribution on all system variables going forward in time. Okay? I start with the first time, I have some joint distribution on the initial variables. I take the policy that gives me some joint distribution at the next step, and so on. Okay? So I can go forward in time and compute the joint distributions on these system variables. There's a typo here. Somehow these pi's have gotten shifted by 1. This should have been pi 1, this is pi t minus 1, and this is pi t. Okay? That part is important. So this gives me a Q function and a distribution, but I can't use this Q function to do optimization. Okay? Because this depends on the overall state. This is the state of the environment, and the agent does not have access to the state of the environment. Okay? So what I'm going to do now is I'm going to take this Q function, and I'm going to take this joint distribution, and I'm going to average out the environment state with respect to this joint distribution. Okay? So I'll construct an averaging step where I look at the QT. This only depends on future policies. I look at xi t, which only depends on past policies, if you fix my typo here. And therefore, I'll define an average Q function, which averages out the Q with xi for every given y and z, where I'm taking a conditional distribution according to that joint distribution. Okay? I get an object which is now a function of what the agent observes, and have to choose actions for the agents. So I can use this to choose the policy of the agent at time t. Okay? So I do this. This gives me a local greedy update. Now, the key property of this local greedy update is that I can show that if I start with a particular policy, pick any time t, and update the policy at that time t, that improves the overall performance of the system. Okay? So I get an algorithm which leads to monotonic improvement. So I keep doing that. Okay? I start with an initial policy, I keep updating the policies at one step at a time, and I continue. And I can show, since the performance is improving monotonically, I will converge. And if I take any limit point of the policies along this convergence, that limit point will be locally optimal. Okay? So I get a local best response or an equilibrium property from this solution. Okay? Great. Let's test it out. So took a bunch of POMDP environments, tested it out within a model with 1-bit memory. It works in few cases, but in most cases it gets stuck in a local minima. Okay? What is going on is that when I start taking greedy best response, I start getting deterministic policies, and therefore the beliefs that I am taking do not have full support, and I don't really explore all parts of my state space. I mean, it's not a learning algorithm, but that's kind of still the intuition that we have. So the obvious fix is keep the policy stochastic. There are different ways to keep the policy stochastic. Simplest is to use conservative policy iteration. Whenever you find a new policy, you don't simply change to that policy. You do a mixture between your current policy and the new greedy policy. Rest of the algorithm remains the same. We continue to maintain monotonic improvement guarantees. And the choice of this mixing rate could be either something constant, or you are doing averaging, which gives you can do like 1 by k, which gives you averaging of the all past policies, or you can do if you take it equal to 1, you get the previous lack of conservatism type of thing. Okay? Once we add this fix, we get this improvement. So you see, what I have now is I have a deterministic algorithm. Given initial conditions, it will converge to something. I'm starting it at different random initial conditions and looking at what are the policies that I get. And since this is a planning algorithm, I can always take the best policy that I found during this search. Okay? And for all of these benchmarks, the best policy is equal to the performance of the optimal policy. While in some cases, we are getting performance better than the optimal policy. What's happening here is I actually don't know what the optimal policy is. I'm giving it to the state-of-the-art POMDP solver to find a good policy, and we are learning policies which are better than what the solver is getting. Okay? All right. So great. Now, the fix is obvious. If I go back to the multi-agent setting, there is nothing in this idea which is tied to a single agent. Everything is going to work in the multi-agent setting in the same way. All I need to do is I need to update the policies in a specific order. Okay? So if I have a 2-agent system, I'll just say, I'm going to go to the terminal time, first update agent 2 at time t, then to agent 1, then go back to agent 2 at the previous time, agent 1. So I fix a particular order, update the policies one by one according to this order, and I'll have the local monotonic improvement, and therefore I'll converge to a local optima. Okay? Let's test this out. So I'm comparing here FB HFVI is a full history-based policy, which does approximately solves the dynamic program. So when I go to certain environments which are large, it basically times out. MAA star is a heuristic search algorithm, which is again based on full history. And I'm trying an algorithm with 1 bit of memory and little bit of conservatism. Okay? So there is no way I expect my algorithm to do as well as the best history-based policies, right? I have at best local convergence guarantees, and I'm just using 1-bit memory. Okay? And it does not do well. It does well in the more complicated environments, surprisingly, but it does not do well in simpler environments. In the very simple environments, it does very, very bad. Okay? And we spent some time trying to understand why is this not doing well. Okay? And I think this environment is representative of showing why this is not doing well. So this is called cooperative box pushing. In this environment, this is a grid world environment with these two agents where the direction of the triangle tells which way they are facing. And there are two types of boxes, small boxes and big boxes. Agents get some reward for pushing small boxes up, and they get large reward for pushing the joint box, bigger box up. The catch is that to push the big box, both agents have to be present, and they have to push at the same time. Okay? So what happens when I try to run this algorithm is, there is a strong local optima which says just push your own boxes up. In order to figure out that they need to coordinate, there is some slippage in motion and so on also. They have to independently figure out we need to go to the center, turn up, push together at the same time, and only then the box will move. Okay? So this is, a lot of things need to happen in a coordinated manner to get this high reward. And they don't have sort of, no matter what initial policy you start with, there is not enough weight at that part of the state space to encourage them to try to do that. Okay? So how do we encourage coordination? The obvious thing is try to bias the rewards towards coordination. How do I bias rewards towards coordination? I use risk-seeking behavior. Okay? So if agents are risk-seeking, they will be willing to try to take the risk to try to get that higher reward. Simplest risk-seeking behavior is use exponential risk with a positive lambda. Typically, these things are used in the risk-sensitive manner or risk-averse manner, where you choose lambda to be less than 0. I'm thinking of this in a risk-seeking manner. So lambda is greater than 0. This is just one option. We have run similar experiments with CVAR and so on. It doesn't seem to be too sensitive to the type of risk metric that I pick, as long as I'm picking a risk metric which encourages risk-taking behavior. Okay? Rest of the algorithm remains the same. So what I'm going to do is I'm going to change my reward function to a risk-seeking behavior, run the algorithm for a while with risk-seeking behavior, and that will give me certain policies. And after doing this initialization, I go back to the risk-neutral setting and run the problem for the risk-neutral setting. So it's going to converge to a local optima for the risk-neutral setting. But the risk-seeking behavior does a good initialization of the algorithm. Okay? So the algorithm is the same, the guarantees are the same. Okay? And we run it on different environments. And what we now find, again, it doesn't do well in the fairly simplistic environment, but in all the other ones, we are getting behavior which is comparable to what one is getting from the best heuristics for the full history-based policies. Okay? This should not happen. I should not be able to get best behavior by looking at one bit of memory. Okay? Our only justification for that is that these are terrible benchmarks, in the sense that these benchmarks are so noisy that in order to get cooperation, you are not using any local information. Going back to that box pushing environment, what ends up happening is I'm not caring at all about what observations I'm making. The optimal policy is spend first time steps trying to go to the center and face up. There will be some slippage and so on. With some probability, both of you would be at that location at the right time. On the fifth time instant, push up. Okay? So I'm simply coordinating on time rather than relying on local information. Therefore, the optimal policy does not depend on history in some sense. Okay? So that's what it is, but it is an algorithm which works. I've been looking at this for 22 years, so I'm super happy that I have an algorithm which I can run on realistic models, or at least benchmark environments, even if not realistic, and it works. Again, the basic idea is when I'm looking at agent state policies, if I fix a policy, the joint process of environment state and agent state is a Markov process. So I can do policy evaluation. I can also compute the joint distribution of all system variables based on policies. I average these two and optimize. Okay? We have ongoing work where we are trying to figure out sampling-based algorithms for this, trying to do this with linear function approximation and so on. So if you have some ideas in that direction, I'll be happy to chat. And with that, I'll conclude, but let me acknowledge collaborators and funding agencies here. So the main work here is in collaboration with Amit Sinha, who was a PhD student who just graduated a few months ago, and Matthew Geist. The work that I presented in terms of approximate information state is based on work of former PhD student Jayakumar Subramanian. The work on designer's approach is what I'd done in my PhD thesis with my supervisor Demosthenes X's. And I'd also like to acknowledge Vijay Subramanian, who has helped a lot in discussion of relation of these equilibrium concepts with concepts in game theory and pointing out to a lot of the good literature, and also acknowledging funding agencies which had sponsored this work. And I'll be happy to take questions. Thank you.
Thank you, Professor, for accepting our request and delivering this interesting talk. Are there more questions from the audience? Thank you everyone for attending and have a great evening. Sorry.
There's a question.
We have arranged refreshments in the coffee hut. Please continue your conversation there. Thank you.
Thanks.